All right, let's start. Let me quickly see what was. So in week 5, you just want to know the definition of a linear transformation, is it? The last topic? Well, that is what we will require anyway. So let's recap that. So what is a linear transformation? A linear transformation is a function between two vector spaces which satisfies certain conditions. So if you have vector spaces V and W, now V and W come with their own plus and dot, correct? So this is a mapping from V to W, meaning a function from V to W. And this has to respect that those two operations. The additional structure that you have on these two sets is that they have a plus and a dot. We'll be using the same plus for both operations of V and W and the same dot for the scalar multiplication of both V and W. It will be clear from context which plus is being used. But anyway, let me write that down first, only then it will be clear. A map T from V to W such that T of V1 plus V2 is TV1 plus TV2 and T of CV is CT of V. This is for all V1, V2, V in V and C in R. So beyond the technical formulation, what is happening over here? If I take two vectors V1 and V2 and then add them in V. So this addition is happening in V. V1 plus V2 happens in V, correct? If I add the vectors and then take their image, that should not be different from taking the image of the vectors that we started out with and adding them in W. So this plus is actually in W, but this plus is in V. Okay. V and W belong to Rn. No, V and W are vector spaces. They could be Rn. I'm audible, right? To everyone clearly?
Sir, is the dimension same for both?
Not necessary. There's nothing over here that depends on the dimension. No? So you add the vectors and take their image, or take the image of the vectors and then add them in W. Both will give you the same answer. So that is what a linear transformation is. So it respects, in some sense, the addition
Sir,
property. The same thing for scalar multiplication. Yeah.
sir, second part that TV1 plus TV2, the addition is in W. In that part, I
Yes.
didn't understand how.
So when you take a vector and take the t of that vector, where does is it? It's in W, right?
Yes, sir.
So
Okay,
this
sir,
is a
got it.
function from V to W. So you take the you look at the image of some element in the domain, you will get an element of the codomain or the range, as you call it, I guess.
Right, sir.
So in this case, the codomain is W. So this guy is in W and this is in W. So what does something in W plus something in W mean? It has to be the
In
plus in
W
W,
only.
right?
Right, sir. Got it.
Yeah. So you add the vectors in V or take the image, or you take the image and then add the vectors, it's the same. The same thing for scalar multiplication. Where is this scalar multiplication happening? This is happening in V. So you scale a vector in V and then take its image. It's the same as you take the image of the vector and then scale it. So what is a linear transformation? To explain it in the simplest terms, it is a map between two vector spaces such that the vector addition and scalar multiplication is well behaved in the sense of these two formulas. Okay. So typically when you study some mathematical object or mathematical construction, in this case vector spaces, what you do is you have first you study the definition, then you look at examples, And then in the case of vector spaces, we saw what a basis is, which is a simpler way of expressing a vector space. And then you look at maps between mathematical objects. So in this case, we are looking at linear transformations, which is the appropriate class of maps that you have to look at in the context of vector spaces. And I believe linear isomorphism is also covered in week 5,
Yes, sir.
at least the definition.
Yes, sir.
Can someone recall what a linear isomorphism is?
The function has to be both 1, 1 and onto.
Yes, sir. Bijective.
Yeah, which is also called, yeah, bijective. A bijective linear transformation is called a linear isomorphism. So over here, you will have this dimension argument, although it is not obvious yet why that is the case. I'll just tell you that if you have a linear isomorphism between two vector spaces, then their dimension has to be the same. That will be the first thing that we will take up in the content of week 6 as well. So just someone was asking earlier about this. Does the dimension have to be the same of the domain and the codomain? In general, no. But for linear isomorphism, that is a necessary condition. That is not
Uh,
sufficient. Just because the dimension is the same doesn't mean the map is a linear isomorphism. But if the map is a linear isomorphism, then the dimensions of the domain and the codomain have to be the same.
So
Is that
just
clear?
while going through that the internet literature, I came across two terms: so linear transformation and linear mapping. The definition for mapping said that the mapping was from Rn to Rm, and for transformation it was Rn to Rn. The dimension remained same in transformation, but for mapping, the dimension changed. So that's what.
Is this the convention followed in the lecture series posted by Professor Sarang Sane?
No, no, sir. I just went through some internet material. That's
Ah,
what created
I
the
so
confusion.
there will be conflicting terminology. You stick to the one which is in the lecture videos, professor's lecture videos. So typically, a linear transformation, see, Rn to Rm are very special vector spaces. You can have a linear mapping, linear transformation from any vector space to any other vector space. The most common terminology that I have come across is linear operator. When both the domain and the codomain are the same, then we have something called a linear operator. Otherwise, it's linear transformation. But for this course, linear transformation will mean T from V to W. And linear mapping is just something that is from Rn to Rm, the special case of Rn to Rm. All right. So we'll use linear transformation for a general uh, mapping from T from V to W, which satisfies these two properties. And linear transformation, you must have seen typical examples, right? Let's just write some examples. Rotation. I don't know if this rotation was discussed, but dilation must have been discussed, or scaling. These are all on Euclidean spaces. You can look at reflection also. All of these are linear maps. Projection. Even if you don't understand what these transformations are, that's okay. Later on, we'll be doing it in a slightly more detailed fashion. But for now, just know that all of these things are linear transformations. Because, so let's take, for example, dilation. If you have two vectors and the sum of the two vectors, this if you scale this by some constant, it is the same as scaling this by the same constant and then adding the two vectors. So this is something that can be seen. I may not be doing a great job of explaining it visually, but you can relate it with the thing that I was telling earlier, that doing the operations first and then taking the image is the same as taking the image and then doing the operations. You can check it for these particular examples at your convenience. So let's get into the content of week 6, wherein we talk about linear isomorphism between any vector space and Rn. So the result says that If V is a vector space, such that dimension of V is equal to n. So we are dealing with finite dimensional vector spaces. So there is an n, which is the dimension of the vector space V. So what does V is a vector space of dimension equal to n mean? Can someone give me one of the
And
consequences of
linearly
that?
independent vectors are there.
Yeah, but even if there is, you need a little bit more, not just linearly independent, right? There is one more condition that is required. So if I take, for example, Rn plus 1, this also has n linearly independent vectors.
They span the entire space, vector space.
Yeah, so what is the terminology for that? Linearly independent and spanning?
Basis.
Yeah,
Yeah.
basis set.
So you have a basis
Size
of
of base
size
set.
n.
Yes.
Yeah. So if V is a vector space such that dimension V is equal to n, then V is isomorphic to Rn. So typically, when you have an isomorphism in category meaning you're studying some mathematical object. Isomorphism means essentially they are the same. It's just that you're changing the names of these things in some way. Okay, so any vector space of dimension n is in some sense the same as Rn. This is the result. Now let us see how that happens. So is isomorphic means that there is a linear isomorphism from V to Rn. So as we were discussing earlier, V has a basis of size n because its dimension is n. Let's just call it V1, V2, Vn. Now I define a map T from V to Rn such that Vi goes to what would be the natural candidate for this? Any guesses?
E1 or
Yeah,
EI.
this is Vi, so Ei.
EI.
Yeah. So if I map a basis to a basis, so you know that linear transformations are determined by where the basis elements go. Is that a statement that everyone is okay with?
Yes.
Yes, sir.
Okay.
Yeah.
So if I specify a linear transform, if I specify a map between two vector spaces only by giving the image of the basis vectors or of any particular basis set of basis vectors, then it automatically determines the entire linear transformation. This is yet another advantage of working with linear spaces, that only finitely many things you can describe a map between two spaces with infinitely many elements only using finitely many elements. So typically your vector space has infinitely many elements, correct? And if I want to describe a map between, let's say, F is a map between R2 to R2, I have to tell you what every f of xy is equal to. But if you know in addition that this is a linear mapping, all I need is what f of 1, 0 is and what is f of 0, 1 is. Everything else is determined. So this is another advantage of working with linear structures. So in this case, what we do is we take our basis and map it to the standard basis. So the ith element of the given basis is mapped to the ith standard basis vector. This ei is just, if you don't remember,
So
this is
both
in the
for
ith position.
so for both BI and EI, it should be standard basis.
What is standard basis for vi? So vi is the basis that we have chosen over here. Over on the domain, We don't know if it is a subspace of Rn or anything. It could be anything, right? So there we are just starting out with an abstract basis V1 up to Vn. And then we are mapping that ith basis vector from that basis to the ith standard basis vector. Is that okay?
That is transformation only, sir.
Yeah, now that I've specified what the elements where the basis goes to, now you know the entire description of the transformation, right? So if I start out with an what does a typical element of V look like? So suppose V is in V, then how you can write this in a particular fashion. What is it?
We can define it with a certain constant which are not equal to 0 into
Well,
the
they could
element.
be equal to 0 also, because you can express the 0 vector also, right? So
Yes, sir. Right.
any vector can be written uniquely as summation Ci Vi. There are unique Ci's which will give you this because this is a basis. If it is just a spanning set, you will just get, you can express it as Ci Vi, but then the unique thing comes from it being a basis. Now, T of V is nothing but T of, let me write it out as C1 V1 plus so on up to Cn Vn. But what does linearity property say? This says that this is C1 V1 plus C2 V2 and so on up to T of Cn Vn. This is the first property. So if you have a sum inside, if you have the sum as the argument of the function, then it becomes, you can just take T of each of the elements and then sum it up. So that is the first property of the linear transformation that we use over here. So let me write just 1 to signify that we have used property 1. Now using property 2, I can write this as C1 of TV1, so on up to Cn of TV. I can take the scale outside. That is the second property of the linear transformation. But what is this? By definition, this is C1 E1 plus C2 E2 plus so on up to Cn En. Why? Because T of Vi, I have defined it to be Ei. And this is nothing but the vector C1, C2, Cn in Rn. So the complete description of the transformation that we have defined in this fashion is you start out with the basis for the vector space. Since we know that the dimension is n, we get n vectors in the basis, which we call V1 up to Vn, and map the Vi to Ei, the standard basis vectors of Rn, and then any element V is mapped to its coefficient vector, right? Now I claim that this is an isomorphism. The fact that this is a linear transformation is obvious because we have just used this and extended it as a linear transformation. But if you want to check it, you can check it. Verify properties 1 and 2 for this, this assignment. But I'll not do that over here. What I will do is the isomorphism part. So in order to check if this is an isomorphism, what is it that I have to check? What are the two things that I have to check?
Minimal.
No, linear transformation.
Zero mapping to 0 for 1 to 1.
So linear transformation, let us say we have this. Plus, I need something else. What is this that I need to conclude that it's a linear isomorphism?
Bijection.
Yes. So a bijection is what I need. So bijection has two conditions. What are those two conditions?
1, 1 and
1 to 1 and on to.
Yeah. 1, 1 and on to. Right? Now, how do we say that this is 1, 1?
0 mapping to 0 of that.
But is that covered already? The kernel and all that?
The terms have not been covered, but 0 mapping to
Okay. So is everyone familiar with the fact that T of V is equal to 0 implies V is equal to 0 is what we have to prove.
Correct.
So under a linear transformation, under any linear transformation, you know that the 0 vector goes to the 0 vector. That is by definition. But then if 0 is the only vector that goes to 0, then it is a one-to-one map. I think this result is already discussed. So we have to take an arbitrary element that is mapped to 0 and show that that actually is 0. So that's what we will do. Okay, so take an arbitrary element such that T of V is equal to 0. Now T of V is equal to 0, and let's say V is expressed as summation Ci Then what is T of V? As we have seen, it is just the coefficient vector, right? Oh, sorry. This implies that this vector C1 up to Cn is the 0 vector in Rn. But what does this mean? This means that Ci is equal to 0 for all I. And this means that V is equal to 0. Is this argument clear?
Yes, sir.
Yeah. Just to recap, what we did was you took an arbitrary vector, a random vector, started out with a random vector, and such that its image is 0. Expressed it as a unique linear combination of the basis vectors, and we saw that it is forced to be the 0 vector. The image is forced, the coefficients are forced to be the 0 vector. Consequently, the vector itself is forced to be the 0 vector. So only 0 is mapped to 0. Everything else has at least one non-zero coefficient. So that will, the only thing that is mapped to 0 is the 0 vector, which means it is 1, 1. Now on to ontoness. If I have a W in Rn, or let me just call it x1, x2, xn in Rn. So when you are going to prove onto, what is it that you have to prove? That every element is picked up by some element. That is, every element is the image of some element. So I pick an arbitrary element in the codomain being Rn in this case. Remember that we started out with a map between V and Rn. So take an arbitrary element in Rn, and that has to be the T of something. And what is that something? Can you guess?
It should be the coefficient vector from the original vector space we are considering from V.
So give me a V such that T of V is equal to x1, x2, xn.
Linear combination of E1, E2, E3,
You have to do a linear combination of V1, V2, Vn, because here V is a vector from the domain, which is V. So typically, it would be something times Vi. What is this something? If I want the image of that to be x1, x2, xn, what should be the coefficients of Vi?
Can be CI, right? CI, some CI.
It is some Ci in general, yes. So what am I trying to do over here? I'm trying to prove that this map is onto. To do that, I took an arbitrary element in the codomain, which is Rn. I called it x1, x2, xn. And I have to produce an element in the domain, which is V, such that T of V is x1, x2, xn. In general, any
Right.
element of the domain is some linear combination of Vi. So it is some Ci Vi. But if I want that
So do
the
we
image
want
is actually, it
XI by
cannot
VI.
be, this is actually
By
Xi, right? So you see that the image of any vector V is actually its coefficients, right? So if I have a Ci over here, I'll get the coefficient vector C1, C2, Cn. So if I want x1, x2, xn to be the answer, then the coefficients have to be Xi, right?
Yes, sir.
Sir,
Does
there's an
everyone get
implement, sir.
this? Yeah.
Sir, please scroll up little.
Sir, C1 up to Cn is 0 only.
No, C1 to Cn is not 0. So here what I have done in this part is that I've tried to describe what this map T does. Initially, I just said that this determines the whole map. Just sending Vi to Ei determines the whole map. In what sense? I expanded on that over here. Given any element V in the vector space V, I can write it as a linear combination of the Vi uniquely. And using the properties of the linear transformation, what we concluded is that the image of any vector V is the vector in Rn whose components are the coefficients of that vector with respect to this basis. It could be zero, it could be non-zero, it could be anything.
Okay, sir. But in one case, we took it as a 0.
Yes, in one case we took it as zero because that is how you prove one oneness. If you want to show a linear transformation is 1 1, you have to say that the only vector that is mapped to zero is zero itself. Zero is always mapped to zero, but then there is no other vector that is mapped to zero. This is what you have to prove. And to do that, we take an arbitrary vector which is written as summation Civi and map it to zero and conclude that each of the coefficients has to be zero. So there's no way any other vector can be mapped to zero. So that's 1 1 and that is done. Okay, now for onto we are taking a different consideration. So, okay, what do you do when you do 1 1 and onto? So you have a function typically is mapping some element to some element between two spaces, right? If you want to say that something is 1 1, the fundamental for functions without any linearity property, you have to say that
Unique
two elements
pre-image.
don't go to the same element. So you can't have something like this.
Yes, sir. Unique pre-images.
Unique pre-images. But in the case of linear transformations, what happens is you just need to say that 0 has only one pre-image. Because of linearity property, that will force everything else also to fall in line. So I just look at 0. I look at pre-images of 0. I take a random pre-image of 0 and I show that it is actually 0. Then I'm done. And that is what we do in 1 1. For onto, what do we need to do? We need to make sure that there is nothing like this. There is no element which is not the image of anything. So we have to pick an arbitrary element in the codomain over here and then say that there is some pre-image of that. So there exists a pre-image. This is ontoness.
Yes, sir.
For
For
every
every element
yeah,
in codomain.
there exists a unique pre-image. This is 1 1.
Yes, sir.
So this exclamation is unique. So unique pre-image. Let me just call it this.
Yes, sir.
So in other words, onto is there is at least one pre-image. 1 1 says that there is at most one pre-image. Yeah. Any doubts?
In this one, we are mapping this in the onto function. So in this one, if we map the x1 from this, then v1 will be 1 and xi would be the x1. So it maps to x1 kind of.
I didn't get you. Could you repeat that?
For the mapping of this, I mean, what
For the
I mean,
mapping T you're talking about.
yeah. For a particular
Okay.
vector in the
Uh-huh.
in the space where we say it's an image of something, so that one will be transformed with just one and other all will become zero.
So you want to look at what this is? Is this what you're saying?
Yeah, yes, sir.
No, but T of you need a vector from V. So you'll have to give me some coefficients. Let's say T of V1. T of V1 will be 1 0 0 0 0. Why? Because V1 is 1 V1 plus 0 V2 plus so on up to 0 Vn. So when you write any vector in terms of this basis, whatever coefficients you get, that is actually the image of T.
Yeah, yes, sir.
So now if you want some vector T of V such that T of V is x1, x2, xn, what should you start out with? V has to be x1, v1 plus x2 v2 plus xn vn. The
Right.
coefficients of v are actually x1, x2, xn is what we want, and that is how we construct the vector.
Yes, sir.
Yes, sir.
Is
Yes,
that
sir.
okay?
Yes, sir. Got
Yes.
it.
Sir.
Yeah.
Sir, you have written V equal to sigma xi vi for all i's.
Yes.
So my doubt is
Not for
this
all I, but
the
okay. It's a summation. Yeah.
sir?
Summation over I xiv.
Yes, sir. Is this the transformation function?
No, the transformation is T. V is a vector.
Mm-hmm.
Any vector in V is written as a linear combination of the basis vectors. The basis vectors are Vi, and I need to specify what the coefficients need to be so that the transformation takes it to the vector in Rn whose components are x1, x2, so on up to xn.
So my confusion is relating that use of the term xi on the LHS and x1, x2, xn. Are they related somehow? That's where the confusion is coming
They
out.
are the same. So
Okay.
in for an element, suppose you have V in V. Since you know that the basis of this is Vi, V1 up to Vn, every vector can be written as I going from 1 to n, Ci, Vi for some Ci which are real numbers, right?
Yes.
So this is an element of the vector space V.
Yes.
And these are scalars, right? Scalars meaning Ci is in R.
Right.
So where does this element lie? C1, C2, Cn. This is an n tuple of real numbers.
And
Yes.
Rn.
So this has to be in Rn. No?
Yes, sir.
So on one hand, you can look at these guys as coefficients of the given vector, and if you put them together, you get a vector in Rn. You can in any
Right.
vector space, since you're dealing with real
Here,
vector
Vi
spaces.
is
So
the basis vector only, no, sir?
VI's are the basis vector. So this is a vector, this is a
Yes.
scalar. You can
Yes.
multiply a scalar to a vector and to
And
get another
they,
vector, and then you can add them. You're still in the vector space.
right.
So, but then you do the T of that. What I'm saying is that T of that is actually this C1, C2 up to Cn.
So T is
Sir,
basically a transformation of V, right?
It's a transformation from V to Rn.
From V to Rn. Okay.
sir, you're
Yeah.
defining isomerism only, right?
Yeah, we are
Uh,
proving that what we have defined over here is an isomorphism.
oh, okay, yeah. Sorry, isomorphism. Okay.
So to do that, we need to check that it's a linear transformation. It is 1, 1, and it is onto. Linear transformation is immediate, and I'll leave it to you to check. For bijection, or 1, 1 and onto is what we need to check. For 1, 1, we use the property that if 0 is the only element mapped to 0, then it is a 1, 1 function. We use that property to show that it is 1, 1. And to show that it is onto, we pick a random element from the codomain space, which is Rn, and then produce an element in the vector space, which is you just take those components of the arbitrary element that you took. The arbitrary element that you took is x1, x2, xn, suppose. Then you use these xi's as coefficients for the basis vectors and construct this vector summation xi vi, and this will actually be mapped to x1, x2, xn. So every x1, x2, xn is the image of some vector in V, which means it is on.
Sir,
Yes.
uh, I have seen tutorial videos of week 5 where one of the ma'am is like using a rank nullity theorem. She has proved 1 1 or on 2. Can we use that method also?
Rank nullity maybe does not come in week 5. No, does it come in week 5? I don't think so. Rank
Week
nullity
5
comes a
to
little bit later.
week 5 tutorial number 5, sir, or the last tutorial,
Oh, okay, I've
which
not checked that. You
okay,
can use rank nullity once you know a little bit more. At this point,
okay,
you know rank nullity for matrices, but you don't know it for transformations yet, correct?
yes, sir.
Right, sir.
Yeah, so I mean, if you want to solve a problem, you can use any method that is available as long as you know it is correct and that is stated somewhere. That's not wrong, but right now I don't think it is discussed yet. In the course
Yes,
content, I don't think
not
it's discussed.
discussed.
I'm getting a
Yep.
bit confused about, like in the last lecture, Lavanya ma'am had also given in terms like, she had said transformation and then the matrix of the transformation. And then, so I'm not able to relate this to, suppose we wrote it in the form AX equal to B. Here, what is the A would be the V1, V2, V3, right? They would be
But
the A.
matrix of the transformation is also part of week 6 content. No? This is
Yeah.
something that I will be discussing, but has it already been discussed in some capacity?
No,
Uh,
sir. Like a
there
small
was
overview
something.
was given, sir.
Yeah. So we had
No,
it
okay,
like,
okay. Then
2x plus y comma this thing. Then how to make that into a matrix was given, was
okay,
sort of.
that we'll see, but
That
that
is
is not
linear
required to
mapping, sir.
understand this, right?
Okay.
Sir,
Yeah. So
that
right
is
now I'm not
linear
able
This
to
mapping.
relate it to that explanation. So I'm getting a bit confused. Like,
you don't need to relate it to that explanation right now. You don't need to know what the matrix of this transformation is. Well, in this case, it is quite obvious what the matrix is with respect to the given basis, but let's not go there because it's not required. Here we
okay.
are just showing that it's a bijection. And to show that it's a bijection, two things need to be verified. You have to check whether it is injective, which is 1, 1, and surjective, which is on 2, both of which we have done. And now what we have seen is that V is isomorphic to, this is sometimes the symbol used. There are other symbols as well. V is isomorphic to Rn. Okay. Now, as a consequence of this, there is one more thing that happens. Suppose V and W are vector spaces such that dimension of V is equal to dimension of W. Let's call this number, this common number, as some M. Right? Then V is isomorphic. So when you say a vector space is isomorphic to another vector space, it means that there exists a linear isomorphism between them. It does not say all maps between them are linear isomorphism. If there is even one map which is a linear isomorphism between the two, then you will say that one vector space is isomorphic to another. That is what we used over here. We just manufactured one uh, transformation between V and Rn, which is a linear isomorphism. Of course, this is not a unique thing because basis is not unique, right? You can start out with any basis and get different maps, all of which will be isomorphisms if done this way. But that's besides the point. So here, coming back to two different vector spaces with the same dimension, there is always an isomorphism between them. So how do we see this quickly? Is that between V and let's say Rm, there is a bijection F, and between W and Rm also there is a bijection, a linear isomorphism. Let's call it G. Now, can you construct a map between V and W, which is an isomorphism? You'll need some properties of compositions and all that. But can you see how we go from V to W using these two maps?
F of G we will use, sir.
But you can't do f of g, right? Because so if you want to do f of g means the codomain of g
Position
is the
of
same
space.
as domain of f, which is not happening over here. So I need to go from v to w eventually. What I'll do is I will in between come to this rm. what is an isomorphism? An isomorphism means that these two vector spaces are the same. They are just renaming of the elements. They're in a one-to-one fashion mapped to each other. So from any vector v, I'll go to Rm, and then I look at what vector is mapped to this vector. So this is G inverse. If you know this from bijection, so as soon as you have a bijection, you have something called the inverse map, and that is also a bijection. This is probably from math 1 even, inverse of a
Yes,
function.
it's in math one.
Yeah. So, right.
Changing codomain to domain and domain to codomain.
Right. So when you have a bijection, you can go back and forth between the function, between the codomain and the domain. They are essentially the same. So if you want to go from the domain to the codomain, in the case of G, you'll go from W to Rm. If you take the inverse, it becomes a map from Rm to W. This is where the existence and uniqueness of pre-image plays a role. You think about it a little bit, you'll understand. So this map is actually G inverse of F. So this G inverse of F is a linear transformation. This is also a bijection you can check. One composition of one functions. I mean, compositions of bijections are bijections. So F is a bijection, G inverse is a bijection. The G inverse of F is a bijection. And this is a map from V to W. If you don't remember the inverses and the properties of inverses, just go back and check it. But this is the fact that G inverse of F is a linear isomorphism between V and W. Is that clear?
Yes, sir.
Yes, sir.
Right.
Yes.
So if we have to map from W to V, then we will go with the G inverse, G O F inverse.
It will be F inverse of G. Because you first need to take an element from here, go here, that is G, and then go back over here. So the function that acts first comes over here, which is maybe confusing a little bit, but once you get used to it, it's fine. First you'll do G and then you'll do F inverse, but you'll write it as F inverse of G.
Sir, we are going back to the like for V to W. If we want to go, we are going back from Rm to W. That's why we are taking as inverse only, right?
Now, if you want to go from V to W, you are going from V to Rm, which is F, and then Rm
Yes.
to W, which is G inverse. So it is
Yes.
G inverse of F. Like F is first, then you do G inverse of that. So it's like
Yes.
G inverse
Okay.
of F of X.
Okay. The inside left to right,
Typically.
we're going to come out. Yes.
Yeah. So
Yeah.
when you do composition of functions, this is the function that acts first, right? So if you want to do
Yes, sir.
something like this, so this is the first function, this is the second function. Even
Yes.
though when we write over here, you write F over here, G inverse of here, the expression of the function will be G inverse of F.
So the inverse one we all always write at the first, right?
It's not that inverse of, so in general, if you have uh, functions between three spaces, let's say X, Y, and Z, and if you have F1 as this function, F2 as this function, this is F2 of F1, is what I'm saying. In this case, the inverse is coming over here, so you're doing this. You'll do F2 of F1 because this is the first function. So the first function gets acted upon over here, F1 of X, and then you do F2 of F1 of X. So F2 of F1 means F2 is later, F1 is first, even though we write it as F2 to the left of F1. This is just a notational thing that you need to get used to. It's intuitive, but counterintuitive in the usual way that things are.
In general, we write F2 of F1 of X, right?
Yeah. In this case, F2 is G inverse and F1 is F. So it is G inverse of F. And for the reverse map, it is F1, F inverse of G. Is that okay?
Yeah.
Okay. So the usable thing is that if you want to say something is isomorphic, say you want to know whether or not two spaces are isomorphic to each other, in the sense that is there an linear isomorphism between these two spaces, then all you need to check is the dimension of the two things are the same, right? So for example, if I say, let's take some example in R4, x1, x2, x3, x4, something like this, some plane. So the question is this isomorphic? Okay, let's say this guy is W. W is isomorphic to Rn, implies n is equal to what? So this is the question. What is the n such that W is isomorphic to Rn? There is only one.
4, sir.
So the guess, let's see. The guess is that it is 4. Does everyone agree with this?
Yes.
Yes, sir.
So,
Yes, is there any doubt?
yeah, it's 4.
Okay, now let's try to do it. When I say W is isomorphic to R to the n, what does this mean? N is what in terms of W? What have we proved over here? V is isomorphic to R to the n, where n was what?
Basis.
Dimension.
Dimension.
Dimension of V, right? So over here, if we say that W is isomorphic to Rn, then n has to be dimension of W, correct? Now,
Yes,
what
sir.
is the dimension of W?
4.
0.
Length of basis of W.
Yeah, so we need to construct a basis. Any element x1, x2, x3, x4 in the space W can be written as, let's say, minus 2x2 minus x3 plus x4. So I'm just replacing x1 with minus 2x2 minus x3 plus x4, because x1 plus 2x2 plus x3 minus x4 is 0, right? So I can write this way, x3, x4. And this I can rewrite as x2 times minus 2, 1, 0, 0 plus x3 times minus 1, 0, 1, 0 plus x4 times 1, 0, 0, 1. So what do you observe? Every element in W can be written as the linear combination of how many vectors?
3 vectors.
3.
Yeah, and these three vectors are linearly independent is also something that you can verify.
Yes, sir.
So this is actually the dimension of W is 3.
3.
Therefore, n is equal to 3. So this guess was not exactly correct. It is a subspace of R4, yes, but it is not isomorphic to R4. Like if there is a subspace of R4 which is isomorphic to R4, then it has to be the trivial subspace, the trivial space R4 itself, right? And of course, you know that this is not the whole space R4. This is a plane in R4. Whatever plane means, it's a hyperplane in R4. There is one degree of freedom that is removed, as in one of the xi's can be written in terms of the other xi's. So not all points belong to this space W. So it is not the full space R4, but it is a subspace of R4 of one less dimension, and it is actually isomorphic to R3. Is that clear now?
Sir, can you please explain that n equal to dimension of W, sir?
Okay, so
Just
here what we did, the result that we have discussed so far is that if V is a vector space such that the dimension of the vector space is n, then V is isomorphic to Rn. I can write this in a shorter fashion as V is always isomorphic to R to the dimension of V.
okay, both the vector space have to have the same dimensions. That's
Yes, isomorphism means the dimensions have to be same. Over here, I actually tell you that if the two dimensions are the same, then they have to be isomorphic to each other. And if they are isomorphic to each other, then the dimension has to be the same.
okay, sir.
So in the question, what was asked was, I give you a vector space W, and I say that it is isomorphic to Rn, and I'm asking you what n is. And that n has to be the dimension of W, and the dimension of W is actually 3. It is not the whole space R4. There is one dimension reduced because of the equation that is used to define the space W. For a more visual explanation, consider the space R2. And let's take the x-axis. What is the x-axis? How do you describe it as a set?
Y equal to 0.
Yeah, or x comma 0, x in R. This is the description of the x-axis, correct? Now, what is the dimension of x-axis? Let me call this as W. What is the dimension of W?
1.
This is 1, right? This is a line, so its dimension is 1. Or if you want to go the formal route, you can just say that 1 comma 0 is a basis for that. Because every element can be written as c times 1 comma 0 or x times 1 comma 0. So that is, it has a basis of one element, which is 1 comma 0. That's a formal way of doing it, but then just intuitively you can see that this is just a straight line through the origin, so it has dimension 1. So the x-axis W is isomorphic to R. And that isomorphism is something that we can see clearly, right? You can send every element x comma 0 to this element x. And that becomes an isomorphism.
So it's isomorphism to R1, right?
R1, yeah, R1 we just write it as R.
Yeah, fine, understood.
Yeah. So this is the explicit isomorphism, and here, because of the dimension argument also, I'm just saying that everything makes sense. So there is a copy of R inside R2. So this is a common confusion to many people at this point. Is R a subspace of R2? Strictly speaking, no, because R is not a subset of R2, right? R is something like X such that X in R, and this is not a subspace of or a subset of XY such that X comma Y is in R2. So is in R. So one of the spaces has only one component and the other space has two components. So this cannot be the subset of this. But it does. So there is a copy of R. But what do I mean by a copy of R? There is a vector space which is an isomorphism of R inside R2. So that is one more point to note. But the most important thing to take from all of this is that when do isomorphisms exist? They exist when the dimension of the two vector spaces are the same. Okay. So that is the first thing about isomorphism. The second thing we'll take a look at is matrix of a linear transformation. Maybe I'll not cover this kernel and image this time around. In the second session, we'll do kernel and image because the last topic also concerns the same thing. So let's just do matrix of a linear transformation and stop over here today. So matrix of a linear transformation. Let's take an example of, instead of dealing with VW, let's come back to the ground and do something between Rn and Rm, which is most of the examples that you will be dealing with in the course. So let's say 2x plus 3y and x minus 1, something like this. You can check that this is a linear transformation. Now, is this a linear isomorphism?
Yes, sir. Maybe we need to check out with the matrix.
But we have not constructed the matrix yet, right? So,
Yes, sir.
okay, let's take another example. So here I have xy goes to x plus y, x minus y, 2x plus 3y. Is this a linear isomorphism?
No, sir.
No, sir.
Why?
Because we are transforming from R2 to R3, sir.
Yeah. So yeah, at least intuitively, you know that this should not be a linear isomorphism, right? So in this case, which one is likely to always fail? Is it oneness or ontoness? What do you think when you go from a smaller space to a bigger space? Which property fails, one or on?
Onto.
On to, sir.
Yeah, you cannot use a smaller number of elements to cover a bigger space. So, of course, this is not a mathematically rigorously precise statement, but at least this is how you can understand. So, and if I do the opposite, let's say I take a transformation from R3 to R2, there what would fail?
So 1.
1 1, sir.
1 would fail because you are taking more number of elements in some sense and trying to map it in a 1 fashion. You are not allowing repetitions, and that is not possible. All of this, when you study kernel and image, will be clearer. But for now, just know that necessary condition is that dimension of both sides should be same. But over here, in this example, the dimensions are the same. And just look at this sort of expression. I'll just write this as a column vector. If I have, let's say, 2, 3, I don't think it will be 2, 3. It will be, yeah, I think it will be 2, 3. Yeah, this is fine. Consider this matrix and multiply it with xy. What do you get?
2x plus 3y and x minus y.
X minus y, right? So this linear transformation can be written as some matrix multiplied with the coefficient vectors. So this can be written, so T of xy is actually equal to A times xy, where A is a matrix. And this matrix is called the matrix of the linear transformation. So the fact is that this can always be done. At least, I mean, in the case of arbitrary vector spaces, abstract vector spaces, you'll have to write coordinate vectors and all that. But at least and this is not something that is specific for R2 to R2 or the same dimensional vector spaces. You will always get a vector. So let us do another example to understand this clearly. You can always do this for any linear transformation. You can write it as a matrix times the input vector. So suppose I want to write T of xy as A times xy, where A is some matrix. Now this is a 2 cross 1 matrix, and I want this T of xy is actually a 3 cross 1 matrix, right? I'm writing it in terms of column vectors. This thing, here it looks like it's a 1 cross 3, but I want ultimately to write it as a column vector. So I'll write it as a 3 cross 1 vector. So what should be the dimension of this A?
3 cross 2.
Close to.
So it has to be a 3 cross 2 vector. And let us draw the thing for a 3 cross 2 vector. So you have 1, 2, 3, 4, 5, 6. This is 3 cross 2 vector. Now, what are these 6 elements? Can you quickly figure out using the definition of the
2, 1, 1,
column
minus
wise
1,
2,
1,
1,
1.
1.
Minus 1 and 1 1.
1 minus 1, 1. So this transformation also can be written as a matrix times the input vector. So this helps us relate linear transformations to matrices. So in the first part of the course, you studied vectors and matrices. And then when you came to linear spaces, you saw that in terms of a basis, everything can be written just as the coefficient vector. Now, when it comes to transformations, that is encoded in matrices. Now, if I'm given an arbitrary linear transformation, how do I find the matrix of that linear transformation? So what you need to observe over here is, what are the column vectors? What are these column vectors? Do you see some
T of E1
relation
and
with,
T of E2.
right? So if you look at this T of 1, 0, what is T of 1, 0? Just evaluating using this definition.
2, 1, 1.
This is 2, 1, 1. And T of 1, 0, 1.
1 minus
What is
1,
this?
1.
1 minus 1.
So could you explain this thing once if you don't mind? This DO10.
No, this is just an observation that the first column is actually T of 1, 0, right? So T, if I do this T of 1, 0, here I'll get 2, 1, 1. And that happens to be the first column of the matrix of the transformation, whatever I'm calling it. And T of 0, 1, just using the definition, this is 1 minus 1, 1. That happens to be the second column of this.
Okay. Got it.
Okay, so this column is T10 and this column is T11, sorry, T01. So the matrix of a transformation I'll write with respect to the standard basis, and I'll explain what with respect to the standard basis is later.
So basically, we're
we'll
writing
see
this
other
in the
ways.
form of standard basis, right?
This is the matrix representation with respect to the standard basis, but I have not explained where I've used the basis exactly, but I have hinted it using this, but I'll explain it a little bit more. But for now, just take this fact that the matrix of the transformation with respect to the standard basis is the matrix for which of a transformation, let's call it T. With respect to the standard basis, the matrix for which the columns are images of the standard basis vectors. And this is for only Rn to Rm kind of a situation, because standard basis vectors make sense only over there. Now let's take another example to understand this better. Suppose I have something from R3 to R2, which goes like T of. So in order to specify a transformation from R3 to R2, I need to only specify it on a basis, correct? If I tell you what, let's say T of 101 is 10, and then T of 10 minus 1 is 0, 1. Let's say T of 1, 1, 1. I believe this is, yeah, this has to be, yeah, linearly independent. So there's one. So I suppose I say that the linear transformation is defined using these three things. You know that the linear transformation. Okay, let's take this as an exercise also. Now, if I have given if I'm given that T of 101 is 10, T of 10 minus 1 is 0, 1, and T of 111 is 11. What is T of XYZ? I'll give you like 3 minutes maybe. Uh, just do the computation and get back to me. What is T of XYZ?
Sir, regarding the previous part, could I ask, sir?
Yeah.
If we like give input of a basis, will we be getting the matrix which we created? Can we say like that?
The standard basis, yes, but if you give any other basis, you might get something else. No, so if you take 1, 1, and 1 minus 1 as a base, minus 1, 1 as the basis that you start out with, T of 1, 1 will be different. It will be something like 3, 0, 2.
Got it, sir. Only we have
Yeah.
to input the standard basis to get the matrix. Is it some sort of trick sort of thing? Can we?
No, no, no. So for now, take it as a definition that the matrix of a transformation is the matrix obtained by specifying the columns as the images of the standard basis vectors. So what happens over here is if I take an arbitrary x comma y, this can be written as x10 plus y01. We are in R2 to R3, right? Yeah. So if I look at t of xy, this becomes x of t of 10 plus y of t01. So if I want a matrix to satisfy this all the time, I do require this to be the first column, right? So if I have some matrix and I multiply it with x comma y, what will I get? I will get c1x plus c2y, where c1 and c2 are the columns of A. Do you hear what I'm saying?
Yes, sir.
Yeah. So your t10 is forced to be c1 and t01 is forced to be c2, as long as you are working with standard basis vectors. So the matrix of the transformation is something that you get on just by computing the images of the basis vectors and putting them as columns.
Yes, sir. Got it, sir.
Okay, now coming back to the example, has anyone figured out what the expression for T of XYZ is? Okay, maybe I'll give 2 more minutes, like until 9:15.
Sir, could you just show the definition, sir, of the previous question? Yeah, yeah, over here. A bit more.
No, no, I'm not talking about in this case, in this example, I'm not talking about uh, matrix of the transformation or anything. I'm just saying there is a linear transformation which for which I've just specified the value on 3
Yes, sir.
vectors which
I
form a
understood this
basis.
question. You wanted
Okay,
to
okay,
ask
okay,
us
okay, okay.
find
You
the
wanted to look at
explicit.
the.
Yes, sir. Yes, sir.
Okay, cool, cool. Go ahead.
Done, sir. You can go down.
Anyone with any luck? Okay, if not the final answer, at least can you tell me how to proceed?
So we try to find the relation between the standard basis and the given basis. Based on that,
See, if
we
you want
found
to compute t of xyz just from three vectors, since this is a basis, this xyz can be written in terms of this basis, right? You want to write this t of xyz, you want to write xyz as something times 101 plus something times 10 minus 1 plus something times 111. And then you can use the linear space properties.
So this could be this first one. The coefficient could be x as the dimension is coming out to be 2.
The dimension is cannot be 2. No, it's not 2. These are linearly independent vectors.
So sir, we have to take alpha, beta, gamma, and then equate it to x and get the equations, sir.
Yes, you should get the equations, but this is even from an examination point of view. I'm saying that that would be quite lengthy. You can immediately see that this coefficient has to be y because the second coordinate, none of the coefficients will contribute anything. Only the last coefficient will contribute something. Correct?
One will be 2x minus z, something like that.
No, no. Is this clear why this is y?
Yeah, yes, sir.
Yeah, yes.
Yeah, then you can do a two equation solving and say that alpha plus beta plus y has to be x and alpha minus beta plus y has to be z. And these x and z you should treat like constants. X, y, z are constants. Right now, alpha beta is the thing that you have to determine. So you can see that 2 alpha is x plus z minus 2y and 2 beta is x minus z.
Sir, could you do it in a traditional method and could you explain why you have taken the last one as y once again?
Okay, cool. Let us do alpha, beta, gamma. What are the equations? Alpha plus beta plus gamma is x alpha, and the second coordinates gives you that 0 alpha plus 0 beta plus gamma is equal to y, and alpha minus beta plus gamma is equal to z. Do you see now why gamma is equal to y?
Gamma is y.
Yeah, which is the second equation. So what I was saying is, irrespective of what coefficient is over here, when it multiplies to the second factor, it gives you a 0 itself. Whatever coefficient is over here, that also gives you a
Yes, sir.
0 itself.
Yeah. Okay, now I got it.
So the second component, which is y, has to be contributed by the third guy only. So it's like gamma times 1 has to be y, which is evident from the explicit calculation as well. But these are things like trying to use the zeros to get to the answer quicker is always a good strategy, at least from an examination point of view. Okay, so once you have gamma is equal to y, then you will have alpha plus beta plus y. So this will boil down to alpha plus beta plus y is equal to x, and alpha minus beta is equal to alpha minus beta plus y is equal to z. So you add the equations, you'll get alpha is equal to x plus z minus 2y divided by 2, and beta is equal to, you subtract the equations, which is x minus z divided by 2. And yeah, these are not very nice coefficients, but fine. You can write this that way, right? X plus z minus 2y by 2 times 101 plus x minus z by 2 times 1, 0, minus 1 plus what was gamma? Y. So you can verify that this is actually working out properly. But this is how we leave it, because using this, I'll get this as x minus z, x plus z minus 2y divided by 2 times t of 101. What was t of 101? It was just 1 comma 0 plus x minus z divided by 2 times 0 comma 1 plus y times 1 1. Is it clear what I'm doing over here? Did you
Yeah.
understand this step to this step? It's just using the linear transformation property. And now we have to do just the addition. I think it will be x plus z divided by 2 will be the first component. Minus y plus y get cancelled. And then you have x minus z plus 2y divided by 2. All right. Now this is t of x, y, z. So this first part of the problem was recover the transformation using the description given in terms of a basis. Next, let's see what the matrix of the transformation is. To see the matrix of the transformation, one more thing is if you have R3 to R2, or if you the dimension of the matrix of the transformation will be dimension of codomain. Let's say this is V, this is W. Dimension of codomain cross dimension of domain. As we saw over here, this was a 3 cross 2 matrix, right? It's like 3 cross 2. It's codomain cross domain. That will be the dimension always. In this case, this is equal to a 2 cross 3. So we'll get a 2 cross 3 matrix as the matrix of the transformation. So what is that 2 cross 3 matrix? So it has 3 columns. The first column is T of E1, second column is T of E2, third column is T of E3. So what is T of E1?
One zero.
No, T of E1 is not 1, 0. So T of E1, what is E1 over here? Input E1 is in R3.
1 0 0.
100.
So what is T of 1, 0, 0?
1 by 2 comma 1 by 2.
So that becomes the column. That becomes the first column. The first column is the image of the first basis vector in the domain.
Sir, we are inputting the standard basis, right? Like 1 0 0 0 1 0 0 0 1.
Yes, yes. So this
Okay.
is the matrix
I
with
was
respect to the
confused by the
standard
T of
basis.
E1, sir. Okay, okay.
Yeah. So yeah, E1 does not automatically tell you which space it is in, but since it is T of E1, it is you can do T of vectors in R3 only, right? So this is the E1 of R3. So and that becomes a vector with 2 components. Those 2 components become part of the first column. So can you tell me what the remainder of the matrix is?
Zero 1 in the second column.
Sir, what is remainder,
0.
sir?
Remainder of the matrix, as in whatever remains, as in I've not
Oh,
completed
okay,
it.
okay. Okay.
Not a
So
technical
basically,
term.
so basically from this T1 is for x plus z by 2, right, sir?
See, this is the general expression of the transformation. To get the
Right.
matrix, I evaluate, I do these 3 computations. T of 1 0 0, T of 0 1 0, and T of 0 0 1. All right.
Half and
What
minus
is this?
last column.
This was half half. This is
1 1.
0 1,
Sorry, 0.
and the last one is
Half
half.
minus half. Minus half.
Minus. So this is the matrix of, it is also, you can write it as M of t. There is an additional thing to do, that this is in terms of the standard basis. So I'll just write STD, which is for standard basis. Now, did you understand how to compute the matrix of a transformation with respect to the standard basis when it comes to linear transformations of Rn to Rm?
So how you got that x plus z by 2 comma x minus z by plus 2y by 2 from that previous equation 1 comma 0 0 comma 1 and y of 1 comma 1?
So so these are scalars, right? You just multiply these two things. So what is the first component? It is x plus z minus 2y by 2 plus 0 times x minus z by 2 plus y. And that just simplifies to, so this thing is x plus y this plus x minus z by 2 into 0 plus y, comma, 0 times that,
plus
I'll just leave it as 0, 0
Yeah.
plus x minus z by 2
plus y.
plus y.
Okay.
Just simplifying that above expression. And that, so there are two things that we have seen in this example: how to recover the transformation from the description given in terms of a basis, and then how to get the matrix of the linear transformation with respect to the standard basis. Now, I've been saying with respect to the standard basis, with respect to the standard basis. What does it mean to say with respect to some other basis? Let us see what that amounts to.
So would you mind explaining this once again, please? This last part, this matrix transformation.
The last part?
This one.
The matrix of the transformation?
Yes.
So are you okay until this point? Until this point?
Yeah, till this point I'm fine. So.
Yeah, now you got the transformation, right? Now
Right.
I want to compute what the matrix of the transformation. The matrix of the transformation is the matrix of order, dimension, codomain, cross dimension domain. In this case, it is R3 to R2. So the matrix of the transformation will be 2 cross 3, and its columns will correspond to image of the standard basis vectors. And what are the standard basis vectors? 1 0 0, 0 0 1 0, and 0 0 1. Using the description that we obtained over here, we compute what is T of 1 0 0. T of 1 0 0 is half half. T of 0 1 0 is 0 1, and T of 0 0 1 is half minus half. That's clear, right?
Okay. X by 2. Okay. And
Just do x plus z by 2 for 1 0 0, for example. That will just be 1 plus 0 by 2, which is half, and 1 minus 0 plus 0 by 2, which is half. That's half half.
okay, so basically this half. So okay. Got it. Okay, half 0 half. Okay. So basically it's half x plus 0 y plus half z. Okay. Got it. I was a bit confused. Yeah. Fine.
Now it's fine, right?
Yes.
Yeah.
Yes.
And then why is this called the matrix of the transformation? Is because if I take this matrix and multiply it with, so this is the matrix of the transformation, one whose columns are the image of the standard basis vectors. Now, if I multiply this with x, y, z, which is a typical input vector in, consider it as a column vector, input vector for the transformation, what do you get? Can you quickly compute what you will get?
Sir, could you repeat your question?
What does this matrix multiplication give you? That is the simplified version of the question.
X by
So
2,
the
It
equation
gives
which I've
the
already written,
Z by 2,
x plus y by
z
2.
by 2
By 2.
and x minus z plus 2y by 2.
Right, and that is actually the transformation. So every transformation is actually just matrix multiplication, is the underlying principle in all of this. And what is that matrix? You will recover by computing the coordinates of the image of basis vectors. So T of xyz is actually equal to this matrix times xyz. So if you take an arbitrary matrix and just multiply it with an xyz of the appropriate dimension, what you obtain is a linear transformation. What the entire analysis shows is that every linear transformation, it doesn't actually show it completely. I've just done it for Rn to Rm case, but at least in that case, every linear transformation can be written as matrix multiplication using an appropriate matrix.
So this
Is
one, in
that
this one,
statement? Yeah, go ahead.
yeah. So in this one, this thing we are writing that T of E1, T of 100 is half comma half. We are just representing it in this
Yeah.
format, right?
What do you mean? We have this is explicit from this definition.
Okay, T of X, Y, Z.
Okay.
Fine. Got it. Okay.
You have T of xyz. You're just evaluating it,
Got it.
and then it becomes the matrix multiplication with respect to that matrix. But this could be recovered only using this as well, the matrix. I did not need to represent it as a column vectors. I can just look at x plus z by 2 and say that the first row has to be half, 0, half, and the second row has to be half, 1, minus half. So in many cases, the non-standard basis expression will also be useful. So here I'll explain what that is. This is the more general case. If I have a vector, let's say 1, 1 in R2. So what are its coordinates in terms of the standard basis? How do I express it as
1
a linear
multiplied by
combination?
1 comma 0 plus
Exactly. This is
1 multiplied by 0 comma 1.
So the coordinates are actually 1 comma 1. And that actually happens to be the coordinates as well. So to explain more clearly what coordinates are, consider the vector 2 comma 0 in R2. This is, let's write it over here. This is coordinates in standard basis. What are the coordinates of 2, 0 in the basis 1 minus 1, 1, 1? How do I express 2 comma 0 in the basis 1, 1, 1 minus 1? Or 1 minus 1? Well, you need an ordered basis actually. With respect to this order. In this case, the order doesn't matter. But how do I write 2 comma 0?
Adding both of them is enough, sir.
Add them, right? So
Yes,
this
sir.
is, let me call it 1 minus 1, 1, 1. And yeah. So the coordinates is actually 1, 1. So 1, 1 are the coordinates of 2, 0 in this basis. I'll call this basis as beta. So if I say, yeah.
So even 1 minus 1 would be a coordinate, right?
No, 1 minus 1 would give you 0 comma minus 2. No? Coordinates are unique.
Okay.
You said 1 minus 1 or what? 1 minus 1 would give you, yeah, 0 comma minus 2.
Sir, what does this coordinate signify?
Signify exactly.
Yeah, so when you're talking about, let's do it in R2 itself. If I draw an R2 and then I tell you describe the points uniquely. So what is a coordinate system? A coordinate system, let's say 1 comma 1 itself. It says that it is it is 1 unit from the x-axis, 1 unit from the y-axis, right? So this is in the standard coordinate system. It is 1 unit from here, 1 unit from here. If I take an alternative coordinate system, so this is also a coordinate system. This 1 minus 1 would be somewhere over here, and 1 would be somewhere over here. Right? Now, in this coordinate system, your axes are these red lines instead of your standard axis. Right? So actually 1, 0 would be this red vector. This would be like the x-axis. Now,
Okay, the transformation for that.
it's some sort of a transformation. So this is just representing the basis in terms of representing every element in terms of a new basis. So it's like a different coordinate system. So what is a coordinate system? The coordinate system, at least philosophically, should be a way of giving an address to a point, as in you have to describe a point uniquely. So one way to do it is to say that it is 1 unit from the x-axis, 1 unit from the y-axis. But I need not do that, right? I can take any two lines and I say it is so many units from this line and so many units from this line, whatever those lines are, as long as they are linearly independent, which means it is a basis. So this is why basis is so important, that a basis gives you a way of describing every vector, giving coordinates. Coordinates meaning distance from the given vectors. Now, what is distance between a point and a vector and all that? At least I hope you can understand just visually at least. What it technically says is that you can express, you can describe, say, any arbitrary point as a sum of multiples of these vectors, which means it is just the coefficients of the linear combination.
So basically, in this one, since like 1 can be formed by the linear combination of these two bases, so that's why 1 is the coordinate here, right?
Yes, exactly. So this is somewhere over here. This is 1 unit from here, 1 unit from here. And there is only one vector with that description, and that is this vector.
1 and 1, okay.
So 1, 1 just means that with respect to the modified basis, this is where you'll find the point. So if I say 0, 1, what is the vector in normal coordinates which has the coordinate 0, 1 in the new system? Vector with coordinates 0, 1 is what vector? What is found with the description 0, 1? So this is actually 1, 1. Okay?
1.
It's not actually distance from. It is actually component along that should be equal to that. I wrongly said that it is distance from, but it's, so in this case it's like x component and y component are both 1. So in this case it is the component along these axes should be that much. So it should have 0 component along the first vector, which is this one. This is, let's call this guy as v1 and this guy as v2. It should be 0 v1 plus 1 v2. It should have one component, a unit component along v2. And as we have seen, if you vary your 0, 1, if you vary the coordinates, you'll end up spanning the whole space. That is the definition of a basis. Correct?
Sir, a bit confused, sir. Sir, previously you wrote 2, 0 as a linear combination of the vectors in the basis set. So now why are
Yes.
we not doing it for 0, 1? Yeah, why
You
are
can
we
do the same
directly
thing.
writing?
No. I'm asking the reverse question. So here what I asked was, what are the coordinates of 2, 0? 2, 0 being in the normal system, as in the standard basis. Then I found that 1, 1 are the coordinates of 2, 0. Now here what I'm asking is what is the vector with the coordinates 0, 1? I'm not asking what are the coordinates of the vector 0, 1 in the warped system, in the new system. I'm saying consider the vector with coordinates 0, 1 in the new system. What is it in the old system is my question.
So basically, what can be formed? You're asking something like that, right?
Yeah, so this is just 0 times 1 minus 1 plus 1 times 1, 1. And this is 1, 1. Confused still?
Yes, sir.
Not getting it.
Okay. Okay. So if you have a basis V1, V2, let me call this guy as, this basis, let me call it as gamma. If gamma is the basis of R2, let's stay in R2 until we get this thing clarified. Any vector V can be written as C1 V1 plus C2 V2. And uniquely, you cannot have two expressions C1 V1 plus C2 V2 and D1 V1 plus D2 V2. You have to have a single expression. Right? That is the uniqueness of linear combination using a basis. So this, maybe let's use square brackets for now. The C1, C2 are called coordinates of the vector V with respect to the basis gamma. Is that clear? Just forget about everything in the past. Just I'm saying that consider any basis V1, V2. Any vector can be written as a linear combination. You pick its coefficients in that order, and that is called the coordinates of that vector. C1, C2 is the coordinate vector. For V in the basis gamma. Do you understand this?
These are basically the coefficients, right?
Yeah, you just take the coefficients, and that is called the coordinate vector. Visually, it's just that you're looking at how this V1, V2 spans the whole space, and what scales of V1 and V2 you need to use to get the given vector. You
Yes.
remember that diagram that we had drawn where any two linearly independent vectors, we saw that its span can be the whole span is necessarily the whole space. So if you use positive coefficients, you'll get this part. If you use one negative, one positive, you'll get this part, and then negative, negative, you'll get this part and the other part. Do you remember this
Yes.
visual representation?
Yeah.
Yeah. So this is just you're using those coefficients as a way of naming that vector in the given basis.
So basically, in the first one, also in this example, also which you just showed right now, 2, 0. So basically, in
Yeah.
that one also we are considering the coefficients only, right? 1, 1.
Yes. 1, 1 are the coefficient are the coordinates because they are the coefficients of the thing.
Okay.
Yeah, that's why 1, 1. Let me use square brackets for coordinates until it clears the confusion. 1, 1 are the coordinates of 2, 0. 2, 0 is in the normal system. So new coordinate system is just a new system made by basis, but we have effect of the standard system in it. Yeah, see, everything is just a reference. So the reference that we use is x-axis, y-axis. This is very easy to understand. We are in some way complicating this by using another basis and doing another coordinate system. There are places in which such a thing pays off. That I don't think I'll have time to describe where it is applicable. But we are just collecting the coefficients with respect to the given basis instead of the standard basis and calling that the coordinate of the vector, coordinates of the vector. So the coordinates of 2, 0 are 1, 1 because they are the coefficients of that. Now, the second question that I was asking over here is that what is the vector with coordinates 0, 1 in the new system? Like, give me the vector in the old system as per the nomenclature of the old system, such that its coordinates is 0, 1. And that is just 0 times this plus 1 times this, 0 times the first vector plus 1 times the second vector, which happens to be 1, 1 in the old system, in the standard system.
Sir, okay, sir, in this case, we need to know zero correspond to which basis.
0 doesn't change. 0 doesn't change, right? You're not doing any translation.
Okay, we are doing a scalar multiplication, right? Basically.
Not a scalar multiplication also, like, well, if you want to look at it as a transformation, you're looking at the map going from, which takes E1 to V1 and E2 to V2. E1, E2 being the standard basis. You're taking the standard basis to this new basis and then looking at the images over there. But that seems to me more complicated. You just take it as the coordinates of a vector in a given basis is just the coefficients in the specified order, and that will be good enough for you.
Okay, so the order of vectors in beta is fixed.
Yes, it is an ordered basis. This is where the concept of an ordered basis is important,
Okay.
because then coordinates can flip, right? Like 0, 1. If you flip these vectors, 0, 1 would mean 1, comma minus 1. So it has to be in that specific order. It has, the coordinates also have to be listed in this order that the basis is specified.
Okay.
Okay. Just to summarize and move on. When you are given a basis, so in general in a vector space V, suppose V1, V2, Vn, this one let me call it as beta, is a basis. The coordinate vector for V in V is obtained by using the coefficients of V in the basis beta. So if I have a vector V, I can write it as C1 V1, Cn Vn, right? Suppose the dimension of the vector space is n, and I have a basis with n elements in this order. It's an ordered basis. So let me just make that clear. So what are the coordinates of V? That is just this vector C1. This is a vector in Rn, by the way. This is the coordinate vector. So we denote it by V beta. Okay. V beta is the coordinate representation of the vector in this given basis. Now things will get slightly more complicated, but yeah, we have to do it to complete the story. What we do is consider a transformation T from V to W. The matrix of T with respect to basis beta for V and gamma for W is obtained by constructing the matrix whose columns are coordinates of images of beta with respect to gamma. Long statement, very difficult to understand as it is to read, but we'll revisit it after doing an example. Now, consider the same example which we did from it was R3 to R2, I think. The same thing. What was it? 1, 0, 1, 1, 0, minus 1, and 1, 1, 1. 1, 0, 0, 1, 1, 1. Hopefully, I will not make any mistake. This is fine. So this was the transformation, and we found out the matrix using the standard basis. What did we do while doing the standard basis? We figured out what the transformation was using some expressing general xyz as a linear combination of these vectors, and we found the expression for the transformation, and then we used the expression to write it as this first column is TE1, second column was TE2, and third column was TE3. Now in this case, I want obtain the matrix of T with respect to basis 1, 0, 1. This is a basis. I'll just use this basis. For domain and standard basis for codomain. Yeah. So stay with me. Earlier we did with respect to the standard basis, but here we are trying to get the matrix with respect to a different basis. So a different basis can be, you can change the basis on the domain, you can change the basis on the codomain as well. So in this case, the domain is R3. The standard basis for R3 is 1, 0, 0, 0, 1, 0, 0, 0, 0, 1. That can be replaced with any basis. And similarly on the codomain, the standard basis is 1, 0, 0, 1. But I can use any other basis as well. But what do I mean by using another basis? To obtain the matrix of T with respect to some basis, what you have to do is you have to evaluate the linear transformation with respect like you on those basis elements. So in this case, I want the matrix of T with respect to the given basis for domain. So I have to calculate what T of 0, 1, 0, 1 is, T of 1, 0, minus 1 is, and T of 1, 1, 1 is. But fortunately, that is already given to me as 1, 0, 0, 1, and 1, 1. Now, what are the coordinates of this in the standard basis? Anyone?
1.
So this is just 1, 0. Coordinates have to be two numbers, right? Like it's 1 times this. So since we are doing standard basis for the codomain, the coordinates are exactly the vectors itself. Okay, so the coordinates and the vectors are not different. Now, if I want to construct the matrix, instead of doing T of E1, I will do T of V1, where V1 is is the first element of my given basis. Suppose my beta is V1, V2, V3. I'm just calling these guys V1, V2, V3. Here it is. This is V1. This is V2. This is V3. So I have to take the given basis for the domain, evaluate T of those elements, that is T of V1, T of V2, T of V3, and write the coordinates over here. So this is just 1, 0, 0, 1, and 1, 1. So how did I get the columns again? I took the first basis vector, did T of that, and wrote the coordinates of that as the first column. I took V2, I did the T of that, and wrote the coordinates of that as the second column. I took V3, did the T of that, and wrote the coordinates of that as the third column. So this is the matrix of the transformation with respect to the basis beta and standard. Or you
Sir, I'm
can just
having a
write it
small
over.
doubt.
Yeah.
Why did you write the basis again in the brackets? Could you just explain?
Yeah,
One
let
zero
me
zero.
let me give you an extension of this example, and then it will be probably clear. Now, the third part of this. So, yeah, that if you want, you can ignore that for now. But did you understand how we arrived at this matrix?
Yes, sir, that's clear.
Yeah, yeah. Now, compute. There is, I don't think this is standard terminology, but this is to be read as matrix of the transformation T with respect to the basis beta and gamma, where beta is the given basis itself, 1, 0, 1, 1, 0, minus 1, and what was it? 1, 1, 1 was it? Yeah.
Yes.
And then gamma, instead of the standard basis, let me take 1, 1 and 1 minus 1. Okay. Now, in order to compute the matrix of the transformation, what do I need to do? I need to take the basis of the domain, in this case, which is beta, and compute T of 101. And that is already, I don't need to compute anything. That is given to me as 1, 0. But I need to get the coordinates in terms of gamma. And what is the coordinates of 1, 0 in terms of gamma? How do I express this as a linear combination of 1,
1
1 and 1
time,
minus 1?
oh no, half multiplied by half.
So this is half, right? So this vector 1, 0 in the new system is actually half half. T of 1, 0 minus 1, on the other hand, this is 0, 1. What are the coordinates of that?
Minus 2.
Is that okay?
Yes, sir.
The coordinates are actually half minus half. And this is actually 1, 1. I believe it was 1, 1. Yeah, 1, 1. And this is what? What are the coordinates of 1, 1?
0 times the 1 time 1 comma 1 and 0 times 1 minus 1.
Yeah. So the coordinates are 1, 0.
So how
Okay.
like how will
Just one moment. Let me finish this thing. So if I write matrix of T with respect to beta on the domain and gamma on the codomain, so I look at this T of V1. and I write the coordinates. I don't write 1, comma 0. So last time I wrote 1, comma 0 because the vector and its coordinates were the same because we were in the standard system. But in this case, the vector is 1, comma 0, but its coordinates in the given system, in the system of gamma, is half half. Similarly, what would be the second column?
Half minus half.
Half minus half. And this will be 1, 0. So this is the matrix of the transformation with respect to the basis beta on the domain and gamma on the codomain. Just to recap once very quickly, in order to compute the matrix of the transformation with respect to beta on the domain and gamma on the codomain, you evaluate the transformation on the basis vectors of beta in that order, and whatever answer you get, you find the coordinates of those vectors in the system of specified by the basis gamma. And those coordinates form your columns in the order specified by the basis beta. It's maybe confusing right now, but once you start solving problems, once you do a couple of problems even, I think you will get comfortable with this.
Sir, in this one, so for the second one where you have written like half 1 1 and minus half 1 comma minus 1. Yeah. So in this thing you have
This
taken
one?
the yeah. So in this
Yeah.
thing you have taken the coordinate as half comma minus half. Why not half?
Yeah, the half comma minus half is the coordinates of 0, comma 1. No? So the image of the second vector, t of 1, 0, minus 1, is 0, 1. And 0, 1 in the system, in the basis gamma, is written as half times 1, comma 1 plus minus half times 1, comma minus 1.
So no. So basically, so T10. So T101 you have taken the image as 110, right?
No, 0, 1. No? So this is how it is specified over here. T of 1, 0, minus 1 is 0, comma 1.
Okay, this one was not mentioned in the question of what?
No. This exam concerns this transformation itself. I am constructing the matrix of this transformation with respect to different bases. The transformation is fixed.
Okay.
So
Okay.
in this one, since you are mentioned as a standard basis and standard basis for domain and codomain, you are taking it 1
That
0.
was the earlier example.
So
Here the basis for the domain is this 101, 10 minus 1, 111, and for the codomain it is the standard basis.
Which means what, sir? Because in the next sum, the problem you mentioned as gamma, but here there is no mention of basis.
There is no mention of gamma, so the gamma is actually the standard basis. So in the standard basis, 1, comma 0 is written as 1 times 1, comma 0, 0, comma 1. No?
Okay, that's why you put okay. So here 1 comma
So
0.
so the thing is, coordinates of a vector in the standard coordinate system is the vector itself.
Okay.
So if you take any vector x, comma y, just one moment, let me complete this. The coefficients are just x and y, right?
Yes. Okay.
So xy is the coordinates of xy. So that is why I actually wrote it again over here. That is the answer to the question why I wrote it over here. I just wrote that these are the coordinates of that. In this case, it is redundant because it's a standard coordinate system on the codomain.
Okay.
But in this case, the vector that you obtain is 1, 0, 0, 1, and 1, 1 in the three cases. But their coordinates are different. They are half, half, half minus half, and 1, comma 0. And those coordinates are found by expressing the answer vector in terms of the given basis gamma.
Okay.
sir, so in this one basically, so okay, half minus. So in this one, since you have taken as like I'm confused actually in the like, so this T101, this transformation you have taken from above, right? 10.
Yes, that transformation is fixed.
1001. Okay, one. Okay, from this one. And in the second one, sir, you're saying that the coordinate is half comma minus half, right?
For the
For
second
transform.
column, yes, for
Yes,
the
yes.
second basis vector. So how do you express? So the image of t of 1, 0, minus 1 is 0, comma 1, right?
Mm-hmm.
How do
Right.
you express this as a linear combination of gamma? Gamma is in order 1, 1 and 1 minus 1.
Okay.
How do I find alpha and beta such that
So like
this equation is satisfied?
half alpha will be half and beta will be minus half.
Correct? So those are the coordinates.
Okay, 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 okay.
The coefficients
The
of the
coefficient.
basis vectors which have to be used to get the given vector, these are called coordinates of that vector in that system.
Okay, basically these transformations, these one you have taken from the matrix above, right? Got it, got it.
I've not used the matrix from before. I've just used the transformation. I've just expressed each element, the image of each basis vector in a new system, collected the
Okay.
coefficients, and put them together in a matrix. And that is the matrix of this transform.
And so when we are saying like basis, like BASES, those are bases only, right?
Yeah, basis is the singular, basis
Singular.
is the plural.
Okay.
So
Yeah, yeah.
when I write basis, it's just, yeah, sometimes I miss the I and then maybe it's confusing. With respect to basis, so here because I say beta for this and gamma for this, when I'm referring to multiple, I just write basis because that is the plural of basis. I is singular, E is plural.
Yeah, I know. Actually, now it's clear. Actually, this coordinates thing was getting
See, this will not be clear until you solve a problem on your own.
right, right, right.
And that is what you should do. And I wanted to solve a bit more problems, but as usual, I think we overshot. So maybe in the next session for week 6, which will be more than a week later. Okay, it'll be exactly a week later, I think. We'll see more problems for sure. I'll try to finish the remainder of the week 6 content quickly, and then we'll revisit all of this. And yeah, by then your quiz one will also be done.
It will be after the
So
quiz one, week
Yes, it
session
will be
two.
after quiz one. In this week, the remainder, I think, I don't know if there will be a TA session for week 6 tomorrow. I think there will be one. But then you'll have revision sessions where you'll review all the concepts from week 1 to 4 and with the emphasis on problems which you are likely to, as in some modifications and some versions of the problems that you are likely to see in the quiz. That will be discussed. I think Wednesday, Thursday is the revision session schedule, and
Sir,
there will be some.
will we get some extension of time for submission of week 6?